Hi everyone, welcome back. In this video, I'm going to show you how to calculate a volume of revolution by using disks. This is practice problem number 2, so if you want to be stronger than you were at the start of the video, pause and try and make progress on your own. With that said, let's get started. Alright, find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. The very first thing we want to do here is draw each of these curves on the xy plane. All right, first up is y equals 6 minus x squared. That is a parabola that opens downward. The highest point here is 6. Y equals 6 minus x squared. Next is y equals 2. That's just going to be a straight horizontal line. That goes indefinitely to the left and right. This is y equals 2. And that's it. So the area that's bounded between these two curves is this part right over here. So now we're going to be, so this area in yellow that I've drawn is called the area of interest. What I'm going to do now is rotate this around the given line. It's the x-axis in this case. So I'm just going to draw the reflected region. If I reflect this about the x-axis, it's going to look like this, kind of like a open smiley face. All right, so now that I've drawn the reflection, I'm going to choose a random x value, say this one here. I'm going to draw the circle now that goes through the top point on both the top bounding curve as well as its reflection. So the circle is going to look like this. It's going to go all the way around. So this here is my outer circle. Next, I have to draw the circle that goes through the lower bounding curve. So the circle right here. So this disk that has a hole in it is called a washer. In calculus, it's known as a washer, but in physics, it's called an annulus. That's spelled A-N-N-U-L-S. So this is another word we use in place of washer sometimes. All right, so the way to calculate the volume now is we just, the general formula is V equals integral of AX dx. This term here, AX, is the area, and that is the area of this annulus that we've drawn here. The area is going to be the area of the outer circle, so that's going to be pi times the radius, which is the height of the red curve. That's going to be 6 minus x squared, and pi times the radius squared is the area of the circle. And I'm going to subtract from that the area of the hole here. It's going to be pi times the radius. That's going to be the height of the lower bounding curve. That's just going to be 2. So 2 squared, and then dx. Now we have to. The question now is to find the limits of integration that we have to use. We have to look at our area of interest here, and we have to ask, what is the lowest value of x of this area? And it's going to be this value of x here is the lowest. And then what value of x is the highest? It's going to be on the other side. It's going to be this one right here. How do we find these values? Well, we have to recognize that these are the points at which the red and orange curves intersect. So the way we find x is by setting each of these, is by solving these equations simultaneously. So we set 6 minus x squared equals 2. And now we solve for x here. So I'm going to bring 6 to the right side, so negative x squared equals negative 4. Multiply both sides by negative 1 to get x squared equals 4. And if I take the square root of both sides, I get x equals plus or minus 2. So the lowest value of x of this area of interest is negative 2, and the highest value of x is going to be positive 2. These are going to be my limits of integration here. All right, so pi is a common factor in both terms. I'm going to factor that out and pull it in front of the integral. So this is going to be pi times the integral, minus 2 to 2. And then 6 minus x squared squared minus 2 squared is 4 dx. So now it's just a matter of calculating the integral. It's just going to be a polynomial, so nothing fancy. I'm going to expand the integrand. All right, so the first term squared is 36. Twice the product in the middle is minus 12x squared, and then square the last term. That's going to be plus x to the fourth, and then minus 4 dx. So each of these is a monomial. So I'm going to, so the integral, the antiderivative of the first term is just 36x. And now I'm going to, for 12x squared, I'm going to bump up the exponent by 1, so x cubed, and I'm going to divide by that same number. That's the antiderivative of the second term. And now I'm going to do the same thing for the third term. I'm going to bump up the exponent by 1, and I'm going to divide by that same number, and then the final term here is minus 4x. I could have combined the 36 and the 4, but that's okay. No big deal. And my limits of integration are from negative 2 to 2. You know what? Let me just redo that. So I'm going to simplify. So plugging in negative 2 and 2 would be a lot of work. So I'm going to, so first of all, I'm going to write this as pi negative 2 to 2. And now 32 minus 12x squared plus x to the fourth dx. And now, because this here is an even function, I can plug in negative x for x, and it wouldn't change the integrand at all. And because the integral is over a symmetric interval, it'll be the same thing if I multiply it by 2 and just integrate it from 0 to 2. So this is much more convenient because one of the numbers here is 0. So it's less calculation if we just do it like this. All right, so I'm going to integrate this quickly now. So equals 2 pi. This is 32x minus 12x cubed over 3 plus x to the 5 over 5. And this is from 0 to 2. If I plug in 0 for x, it's going to be 0, so I just have to worry about plugging in the 2. This is 2 pi times 32 times 2 minus 12 times 2 cubed is 8 over 3, and now plus 2 to the 5th, that's 32 over 5. So our volume is whatever this is, so I'm going to pull out my calculator now. 2 pi times 32 times 2 minus 12 times 8 over 3, now plus 32 over 5. What is that? That's 384 pi over 5. This is the volume. All right, so that does it for problem 2. Thanks for watching.